Hi, in this presentation I'm going to talk about scientific argument and reasoning. And so the first thing I want to talk about is scientific thinking processes. So the 8 practices of science and engineering that the framework identifies as essential for all students to learn and describe in detail are listed below. Number 1 is asking questions for science and defining problems for engineering. So when you think about science and you think about engineering, science is really about gaining an understanding or knowledge about the universe, our surroundings, rational, logical manner of how things work. It's not necessarily about new technologies. And engineering is really about identifying problems, creating new technologies or new products to make more useful and a better life for human beings. So the engineering component is really taking the science that we know and applying it to a situation or a new product and enhancing or improving life here for us as human beings. Developing and using models. So if we take a look at this second one there, that is our second practice of science and engineering. Number 3 is planning and carrying out investigations. So they need to learn how to plan an investigation, how to carry out an investigation, not just carry out an investigation from what's been planned for them. Sometimes you do have students first carry out investigations and they see how they are set up before they create their own. Okay, and step number 4 is analyzing and interpreting data. Step number 5, using math and computational thinking. Oftentimes science will have mathematical practices or engineering will require mathematical calculations, computational thinking. Constructing explanations for science and designing solutions for engineering. So that's really taking it from an understanding level to an application level. Engaging in argument from evidence, and then obtaining, evaluating, and communicating information. And so I put this on here just because as you're looking through what the framework has, you want to look at, okay, what is the nature of science telling me? What is the nature of engineering telling me? And where are they similar? And so start to identify some of the items that you think are similar that would help you develop students as both a scientist and as an engineer in your classes. If we look at some of the different things, we know that part of science, there are theories and there are models that are created to test those theories. We often formulate hypotheses or propose solutions, collect data by testing our solutions, and then we check to see if it's accurate or not. Okay, in the real world, we are doing all of those things, and it's not always in a scientific method approach, but we're doing many of these different things in different, it's not so clean, it's a little bit more messy. And so thinking like a scientist and then applying scientific knowledge like an engineer does require us to have all of these skills in place. We have to be able to ask questions, we have to be able to observe, we have to be able to create experiments, measure results, we have to be able to do that investigation, and that's part of that there. Throughout that investigation, we have to be evaluating and analyzing information, and then we have to be able to develop explanations and solutions from our results. First, we want to figure out what we think is going to happen, and then we want to test that and see if we were accurate or not. Was our hypothesis correct or not? And we have to be able to have an imagination, but yet also have reason to think through things logically and calculate and predict things. So here are the 5 E's and how are similar types of thinking reflected. So some of the things you want to look about here is we have ask, imagine, plan, create, improve. And so this is in a circle because that's something that we would continually do through processes and iterations and innovations. So really, if you look at innovation, it goes through a process like this where you ask questions, you imagine, you plan, you create a prototype, then you improve on that prototype. And you just kind of keep going through that process. Some of these, the 5 E's here, how will we get students engaged? How will we have them be exploratory? How will they explore? How will we have them expand their knowledge of what they've learned? How will we have them explain what they've learned? How will we have them be evaluating data, evaluating observational data, collected data, things along those lines that then interact with all of these things. And so as you look at it, it would be nice for us to say that it's nice and clean and you go from one to the next to the next to the next, but you don't. It's a little bit messy. Okay, if we talk about scientific argumentation, the NRC framework states chief among these features is a commitment to data and evidence as the foundation for developing claims. The argumentation and analysis that relate evidence and theory are also essential features of science. Scientists need to be able to examine, review, and evaluate their own knowledge and ideas and critique those of others. Argumentation and analysis include appraisal of data quality, modeling of theories, development of new testable questions from those models, and modification of theories and models as evidence indicates they are needed. So when you look at this, some of this would even include peer review. So having students review each other's work and give them ideas for enhancements and improvements, things along those lines. Another part of it really is about being able to examine and review your own knowledge. It's about developing new testable questions. You'll notice there's a lot of things similar to the scientific method in here. Tips to encourage successful student responses. So as a teacher, you're going to be facilitating some discussions. You're going to be helping students think through their thought processes. One of the things that you can do is you can have students call on other students. So if a student answers a question, then it can be their option to pick which student gets to answer the next question or give a point of view in the conversation. Another way to do this is to have popsicle sticks as well. And you can just select random students out of there. One of the challenges you'll have is making sure that you include all students in these conversations and not just the ones that raise their hands or dominate the conversations. You want to encourage students to defend their reasoning against different viewpoints. Whether you think they're right or wrong, they should be able to state a viewpoint and then defend it. You want to ask students to describe how they arrived at their answer. So again, you're asking them to think, okay, so you have this certain viewpoint. Why do you have that viewpoint? What evidence supports your viewpoint? Another thing you can do is call on students randomly. Like I said, you could use the student names and a popsicle stick. You can use a name generator, something along those lines. Let students develop their own questions for part of the discussion. Assure the students that there is not a single correct answer to their questions. Here are some additional tips to encourage successful student responses to questions. Remember to provide at least 3 seconds of thinking time after a question and after a response. It's often good to actually count inside your head. Otherwise, those 3 seconds will go by pretty fast. Allow individual thinking time, discussion with a partner, and a class discussion. So some of the things that you can do is just tell them to sit and think for a little bit about it and maybe even jot something down on paper or to turn and share with a partner. Sometimes after you have them share with a partner, you can have the partner tell the class what the other person had said. Ask follow-up questions, for example. You can say, tell me more. Or you can respond to a student's answer in a non-evaluative fashion, such as, I appreciate your thinking. You want to have it so that they are having a positive experience and they're encouraged to continue to participate. Ask for a summary to promote active listening. So you could ask other students to summarize what another student had said. All right, so some talk moves and examples. These 6 productive talk moves help students clarify and expand their reasoning and arguments. So one of the things is revoicing. And so revoicing is simply saying something like, so let me see if I've got your thinking right. You're saying X, Y, Z. Asking students to restate someone else's reasoning. So, they'd be actively listening and then having to restate it. Can you repeat what he just said in your own words? So now you have to internalize, take what was said by somebody else and now put it into your own words. Asking students to apply their own reasoning to someone else's reasoning. So do you agree or disagree and why? What were the good points of their reasoning or their argument or what things might you challenge? Some other additional talk moves would be prompting students to further participation. So you could say, would someone like to add on to what so-and-so had said? You can ask students to explicit their reasoning. So what we mean by this is, why do you think that? Or what evidence helped you to arrive at that answer? Or say more about that, please. Using wait time. You can just say, take your time, think through it. We'll wait. Not a big deal. Try to relieve the stress and pressure. So hopefully you found some of the information in this presentation helpful, and look forward to seeing what you develop in some of your lessons down the road from it.